Our last topic of the semester is galaxies. All of them. So essentially, the whole universe. The whole universe is composed of galaxies. In this background image from the Hubble Space Telescope's Ultra Deep Field Survey, every thing that you see on the screen is a different galaxy. One of the most amazing things that we've learned from the Hubble Space Telescope is you can point it pretty much at any dark spot in the sky, and if you leave it there long enough and collect enough light, you will see an image like this, where it's entirely populated by galaxies. In any direction you point in the sky, there is a galaxy. It's hard to imagine how many galaxies that means, but we can put some numbers on it. There are about 100 billion galaxies in the universe. And in each of them, there's about 100 billion stars. If you remember from the previous lecture on the Milky Way, there was about 250 billion stars. So the Milky Way is kind of a bigger galaxy. It's on the bigger side. There are some like Andromeda that has trillions or more stars. So the Milky Way is not the biggest, but it's a little bit above average. The average galaxy contains about 100 billion stars. So 100 billion galaxies, 100 billion stars in each galaxy. If you multiply those two numbers together, you get 10 to the 22 stars in the universe. So I wanted you to kind of take a second to absorb that information. This is 10 to the 22. So a 1 followed by 22 zeros. Now you might look at that and just say, that's huge, that's really big. And we do that a lot in astronomy. We get these numbers that are so large. So I wanted to think about a way to convey the size of it, both to you and to myself. How do I wrap my mind around that large of a number? Well, so what I settled on was, if a person lives for 100 years and you visit a different star every second of your life, so 100 years and every second you're visiting a different star, you'd only get to see, 3,155,760,000 stars. Well, how does that compare to all the stars in the universe? It's about 0.0000000003% of the stars in the universe. So basically nothing. You will have seen almost none of the universe if you spend 100 years of your life visiting a different star every second. So then I thought, well, could we get to know the Milky Way? Let's say you did this in the Milky Way alone, just in the one galaxy, and tried to survey as many as you could of the 250 billion stars in a galaxy. Well, then you'd achieve only about 1% of the stars in just the Milky Way alone. So if you spent your life looking at a different star every second, and you just stayed in the Milky Way, you would see about 1% of the stars in the Milky Way alone. That's just unimaginable how many stars there are in the universe. But hopefully that gives you a little bit better sense that the universe is really big. So it got a lot bigger when we discovered galaxies. Before that, everything was assumed to be within the Milky Way. The Milky Way was the universe, not just our own galaxy. It was the universe. But in 1924, Edwin Hubble, who's really the star of this lecture, a lot of the things we're talking about are things that Hubble worked on. You kind of call him like the godfather of galaxy astronomy, galactic astronomy. And what he did that really extended the size of the universe was to look at these objects that were called nebula, but that he could resolve a couple individual stars within them, and by identifying Cepheid variables, measure their distance. And when he did that, the distances were so extremely large, larger than any star that had ever been surveyed in the Milky Way, that he could only come to one conclusion, and that's that these nebula are really outside of the Milky Way. They're an entirely different thing. They're self-contained objects outside the Milky Way. And so that's really the birth of galaxies. That we were able to place these nebular looking objects so far outside of the Milky Way that they had to be something different. And in fact, now we know they are their own galaxies. One of them that he measured was this one, which we saw last time. This is the Andromeda Galaxy, or we know it now as the Andromeda Galaxy. It was originally one of many nebula that were visible in the sky, and it was given the catalog number M31. You probably will see M31 listed on the star charts that you look at. M, if we haven't talked about this before, M stands for Messier. The Messier catalog was a catalog of all the known nebular objects, things that were not stars or planets or moons, that could be identified in the night sky. Sort of a collection of things that were interesting to look at that weren't like the rest of the stars. And so M31 was this object. Edwin Hubble had finally had a powerful enough telescope to resolve some individual stars in it, found Cepheid variable, used it to determine the distance to the Andromeda Galaxy, among others. And from there, we got a much bigger universe. Now, we talked a little bit about the types of galaxies last time, so this is mostly just a recap. There are spirals that we divide into barred and unbarred. So this is a barred spiral. This is an unbarred spiral. The bar refers to the fact that you can kind of draw a line across the middle. Then there are elliptical galaxies that are basically just round and you don't see any spiral structure. They're almost smooth looking like eggs. And then we have irregular galaxies. That's the catch-all category for everything else. The two most prominent irregular galaxies that we can observe, well, we can't, we're in the northern hemisphere, but our friends in the southern hemisphere can observe, are the small and large Magellanic Clouds. And this image here, taken from the southern hemisphere, shows you the small Magellanic Cloud and the large Magellanic Cloud alongside the Milky Way. If you are able to observe the Milky Way, when you do your sky observation, or you have observed it, you should notice that when you look at it in our sky, it's angled the other way. That's because the difference between the north and southern hemisphere, right? In our sky, it's angled this way. In their sky, it's angled that way. And that's just the difference in our perspectives. Okay, Hubble went on to, after discovering these galaxies, classify them, right? So we have all these objects now that are outside of the main Milky Way galaxy. What are they like? What kinds of shapes do they have? And can we group them together? And so he started to create this categorization, this classification scheme for ellipticals and ellipticals and spirals. And you can see that the ellipticals basically go from perfectly round to more oblong looking, and spirals can be stretched in different ways, and our viewpoint on them can be different. The barred spirals can be a little bit more coiled, or really just two spiral arms, maybe a little more amorphous. I'm not expecting you to be able to subclassify these galaxies, but just to know that there is variety within each of the major types of galaxy. So within ellipticals, there is some variety that astronomers do distinguish, and the same with spirals. Now, for the major types, we can look at the similarities and differences. Spirals have certain similarities within themselves. Their mass ranges tend to be 10 to the 9 to 10 to the 12 times the mass of the sun, whereas ellipticals, the range is bigger, right? So you have ellipticals that are much smaller and ellipticals that are much larger than spirals. And irregulars are kind of in between. In terms of size, Spirals have a fairly narrow range compared to ellipticals, 15 to 150,000 light years. Ellipticals from 3,000 light years up to greater than 700,000 light years. So this table gives you some sense of how how much variety there is which within each of the categories, and also how they compare to one another. Ellipticals, for example, are all old stars, whereas spirals or regulars can be a mixture of old and young. Now, if you think about the last slide from the previous lecture, how someday the Andromeda Galaxy, which is a spiral, may crash into, or we expect it to crash into, the Milky Way galaxy, 3 billion years from now. Well, it might give you some sense of why this makes sense. Spiral galaxies like ours have a mixture of old and young stars. When they become ellipticals, they're having gone through the process of colliding, spent some time as irregular galaxies, and then eventually evolved into a smoother, more egg-like shape. So if that's the tendency for how to form an elliptical galaxy, then it would make some sense why they would be the older populations of stars, whereas spirals, a mixture, irregulars, still a mixture. In fact, during the collision, you'd expect that it triggers some new star formation, but by the time they evolve into elliptical shaped, they will mostly be old populations of stars. Okay, other things that are important on here, interstellar matter, gas and dust. A lot of gas, some have a little dust, some much dust. So a pretty wide range with the irregulars. In ellipticals, almost no dust and little gas. So again, thinking about this as a process of evolution, that makes sense. By the time they get to be ellipticals, the dust and gas may have been used up, right? It may have been used up and to create these younger stars that eventually evolve to become older stars. And then the last ones are about this idea of mass to light ratio, how much mass it has relative to how much light it's putting out. There are differences in that category. This is just looking at the visible light, and this is looking for the total light, so including all parts of the spectrum. Now, it's interesting that in the visible light, you see differences between them, but in the mass to light ratio for the total galaxy, spirals and ellipticals are about the same. So they may be putting out, for example, more visible light in elliptical galaxies, but the spirals compensate for that by putting out more light in other parts of the spectrum, right? So if they have younger stars in them, that means they're going to have a lot of like blue stars, which are very high energy, so you might be getting a lot more of the small wavelength light. So some of its energy may be contained in the small wavelength light. But when you average it all out, spirals and ellipticals put out about the same mass to light ratio of about 100. Okay. Now, Hubble had a nice telescope for his time, in fact, the best telescope for his time. But since then, we have got better telescopes. The best telescope we have in space is the Hubble Space Telescope, at least until the James Webb is launched someday, hopefully in the next year or two. But for now, it's the Hubble Space Telescope, named after the very same Edwin Hubble. And so we have been able to continue or build upon the measurements that Hubble made of these galaxies, find Cepheids, and also find type 1a supernova. So on the left, we have an example of a galaxy where a Cepheid has been observed. You can see the Cepheid get brighter. So this is May 4th, May 9th, May 31. You can see its brightness changing. Cepheids have the period luminosity relationship. They're standard candles, and we can use that to determine the distance of this galaxy. even more precisely now than Hubble could in his time. And then supernova. These pictures are always just are mind-blowing. This is in this galaxy. It's sort of in the outer part of this galaxy. This is a single type 1a supernova. So it was a low-mass star, became a red giant, became a white dwarf, had a binary companion, and eventually became a supernova when it had accreted enough material from its neighbor. That explosion was so bright that its light is every bit as intense as all of the light from this galaxy, from the entire galaxy. So let's say this is an average galaxy, 100 billion stars. This one star was as bright as all 100 billion stars there combined together. Type 1a supernovas, again, are standard candles. So when we see them, we can then determine the distance to that galaxy. And now we can do that much better than Hubble was able to in his time. Okay. Now, before even Hubble did his work, it was known that these nebulae had pretty strong redshifts. So they were not called galaxies yet, but they had strong redshifts. That means they're moving away from us. Remember, redshift is moving away, blue shift is moving towards. These nebulae all had pretty strong redshifts, except with a couple of exceptions. And that was just a mystery. Well, now if you factor in that these are galaxies, now we can say that galaxies have really strong redshifts. At least most of them have really strong redshifts. Galaxies appear to be moving away from us. So one of the important astronomers in this time was actually a Belgian priest named Georges Lemaitre, and he proposed, based on this evidence, that the universe was expanding. He was a very good mathematician, and he was able to explain using Einstein's theory of relativity that was consistent, that the universe could expand in that theory, and it was consistent with the evidence from these nebulae / galaxies. And so that was the origin of the idea of the expansion of the universe. Hubble went a little bit further, collected more data, along with a colleague named Milton Humason, who has an interesting story. You should take the time to read a little bit about his background in the textbook chapter, but I'll leave it at that. So the two of them together made measurements of how fast the galaxies are moving away, so they're what's called their recessional velocity, and then compared that to their distance measurements that they had been making. And Hubble did this alone in 1929, and then again extended out to farther and farther distances with Humason's help in 1931, and you can see the results in these plots. As you go farther away, the recessional speed gets faster. Okay, and this is even farther away, the recessional speed gets faster. You can see the red dots down here at the bottom. Those are these red dots. And that's a pretty clear relationship. And it's now known as Hubble's law, that recessional velocity is proportional to how far away the object is, how far the galaxy is. And the constant of proportionality is known as the Hubble constant. Okay. Now, the Hubble constant, or the Hubble's law, gave us a new way, an incredible new way to measure the distance to galaxies. Because all that you need to measure the distance to a new galaxy is its redshift. And that comes from its spectrum. If you can see the galaxy, you can get its spectrum. You can see what its redshift is by looking at specific lines in the spectrum and if they're not where they're supposed to be. You use the equation that we've encountered a while back to go from that wavelength shift to the speed. And now Hubble's law tells you how to calculate the distance, because it says speed is Hubble constant times distance. So Hubble constant is a constant. If you know that and you measure the speed, you can calculate d. You can calculate the distance. And the only limitation to using Hubble's law is that you need to be able to see the galaxy. So Hubble's law essentially gives us a way to measure the distance to any galaxy that we can see. If we can see it, we can take its spectrum, we can measure the redshift, we can determine the velocity, and we can calculate the distance. And it turns out that extends how far we can measure out to 13,000 million, otherwise known as 13 billion light years. So we can determine the distance to galaxies out to about 13 billion light years. As long as we can see it reasonably well, we can get that data. A couple of these we've talked extensively about: Cepheid variables, type 1a supernova. Those ones we've covered before. The Tully-Fisher relation, planetary nebula, are other ways. There are explanations of this in the textbook. I haven't gone into much detail, so I'm not going to spend any time with it. But there are other ways to estimate the distance to things. They all boil down to the same thing. Can you determine luminosity? You get luminosity, you compare it to apparent brightness, and that allows you to find distance. Okay, so now we come to like the theoretical side of the Hubble law. It's a very practical relationship. It's empirical, based on the data. But what does it mean? What does it mean that that more distant galaxies are moving faster away from us? It means that the space between the galaxies is expanding. And it's important to distinguish that from galaxies moving through space faster. The galaxies are not, so if that's what you're imagining, the galaxies moving through space, that's not exactly what's happening. What's happening is the space between them is expanding. And there's a way to think about that. There's two models here. One is in one dimension. This one's a little easier to think about, but then you can also extend it to 3 dimensions. And one of the homework questions will help you, I think, get the idea of this a little bit more when you actually work through the math. So here are some ants on a ruler. The ruler gets bigger. The ants are staying in the same places, but the space between the ants is growing. Now, if you compare this image to this image, so let's call this ant 1 and this ant 2. Ant 1 and ant 2 are now this far apart. They used to be that far apart. So if this ruler doubled in size, then they used to be 2 away, like 2 steps away. Now they're technically 4 steps away. But this one here, ant 4, was originally 10. So now ant 4 is 20. So if this thing doubled in size in 1 minute, then what happened with this ant compared to this one is it grew, or it got further away at 10 centimeters per minute, whereas this one grew at 2 centimeters per minute, or got further away at 2 centimeters per minute. The point here is that when you have things fixed to the space and the space expands, farther things away from you are moving away faster than things that are closer to you. Okay, even though the space is expanding linearly, it's like the things that are around you are not moving away from you evenly. It can be hard to really understand that. You have to, I think through the math of it. And so that's why the last question on the homework assignment is asking you to actually do the math for a similar example like this. Now, obviously, we're not in 1 dimension. We have 3-dimensional space. So a better picture is this raisin bread model, where the raisins represent galaxies as the dough rises, the bread expands, and because of that, the space between the raisins expand. Now note the raisins are staying the same size, but they're getting farther apart, and the speed at which they're getting farther apart increases with how far away the raisins were originally. So if we take this idea a little bit farther, but go in the other direction, not think about the universe expanding, but we can imagine that if it expands now, it must have been closer together in the past. That's what suggests to us the idea of the Big Bang, right? If things are flying apart from one another, so to speak, then there must have been an event in the past that led to that. And we call that event the Big Bang. And we can estimate when it might have happened. So think about Hubble's law again. In the equation form, this is what it looks like. Speed, or velocity, however you prefer to say it, is h times d. But speed is also just distance over time in general. This is distance, so that means this has to be over time. It has to have units of 1 divided by time. So if we take the inverse of this number, this Hubble constant, we get a time. And that time is the estimated age of the universe. Now plugging in the numbers for current estimates of the Hubble constant, that time turns out to be about 14 billion years. So just extrapolating backwards, at the rate things are flying apart now, the Big Bang must have happened about 14 billion years ago. So you'll hear people say that the universe is 14 billion years old. This is what they mean. It's an extrapolation from Hubble's law using how fast things are flying apart now and imagining going back in time to when they were all together. If we had more time, we'd go into a lot more detail on the Big Bang and what happened and ideas about the shape of the universe and everything, but unfortunately, we are coming to the end. But I do want to leave you with one more mystery to finish things off. I couldn't end the course without at least mentioning this one remaining mystery, because as you'll see, it's a kind of big deal. So let's think back to the Hubble graph, distance and velocity, nice straight line. But is it perfectly straight? Maybe it curves up. Maybe it slightly curves down. What would you expect it to do? So consider gravity. After the Big Bang, galaxies are getting farther apart, but gravity is always going to want to bring them back together. That's what gravity does. The matter curves space. That curved space is going to cause the objects to pull back together, to slow down. Okay. Now they might be moving fast enough. If the Big Bang was powerful enough, then things could reach their escape velocity, right? The escape velocity is fast enough to escape the gravity that's pulling things back. Maybe galaxies reached escape velocity. If that's the case, the universe will continue to expand forever. If it's not the case, gravity may eventually turn things back around. And who knows, maybe far into the future, there's a big crunch coming that's sort of the opposite of the Big Bang, where the galaxies have all contracted onto one point and collided into something. People like this idea because it could lead to the possibility of a cyclical nature of things, that there's always a Big Bang and then eventually turns into a big crunch, which then leads to another Big Bang, and so universes could cycle like this forever. But whatever the case may be, we have a certain understanding that gravity should slow things down. That should bend the curve down. Now, it might not be enough to turn it around. They may have escape velocity, but it should bend the curve down. Well, let's see what it does. When we take a look at the best data available, we're looking at these red dots here. The black line is like the critical level, right? If it was on the black line, it would continue to expand forever, eventually slowing down to zero, but it would continue to expand forever. It would never turn back around and result in a big crunch. The blue line and below would be for a decelerating, so it's slowing down. This is what we'd expect, right? This is the curve bending down very slightly. But that's not where the data are found. They're found on this reddish line. Maybe it's orange. This line. They tend to be above that critical value, and that means that they're accelerating. The expansion is accelerating. The graph is actually curving up. There's no explanation for this, or at least no good one. There's no good explanation for this. If anything, we fully expected the expansion of the universe to be slowing down. For it to be accelerating means that something must be pushing it to expand faster. And we don't know what that thing is, but something must be there pushing it. We now call this thing dark energy. So sort of like dark matter was the material around galaxies that are making stars at the outer edge of the galaxies go faster than we'd expect them to. And then dark energy is essentially pushing galaxies away faster. There's no explosions that ever work like this, right? Explosions don't get more powerful the more time goes on, right? There's a big explosion at the beginning and then it fades away. That's what you expect. This is completely different. Interestingly, Einstein actually had this idea, and he had a term in his equations for what would be dark energy. And then he immediately said, oh no, that's crazy. And he called it like the biggest mistake of his career. Well, he may not have been exactly right, but it turns out that that term needed to be there. There is something called dark energy. And now we just need to figure out what it is. And we need to because it's a huge amount of the universe. In fact, we estimate about 68% of the universe, of the energy and matter content of the universe, 68% is dark energy. And we don't know what it is. So that's where we'll end. We know what ordinary matter is. Almost everything we've talked about in this course is ordinary matter. When you tally up the total, so ordinary matter is mostly hydrogen and helium and stars and other stuff like people. That's only 5% of the universe. There's a lot left to learn. We need to know what dark matter is. But even knowing what dark matter is, most of the universe is dark energy. So until we know what that is, we won't have a complete understanding of everything. So that's it. We'll end right there. And yeah, thank you for bearing with me all this time. And I hope you learned something and have some enthusiasm for astronomy, and will think about these things every time you look up to the night sky.